Hello friends and welcome to another example video. In this video, we will talk about what is eddy current and apply laws of electromagnetic induction, which is from chapter 23 in your A-level syllabus. We will look at Lenz's law, Faraday's law, and also the reason why we pick such a old example is probably because eddy current and the idea of inducing current in a body or a metal body like a metal disc is pretty important. We use this in brakes, when we brake cars or when we have brakes for any kind of vehicles with large masses. Okay, so this is a pretty important application. So let us begin by seeing what is this example about. So here we have a metal disc. It is swinging freely between the poles of an electromagnet as shown in figure 5.1. So these are pole pieces, this one and this one. Okay, so you might be wondering, is it important to know which is the north pole and which is the south pole? Yes, if you want to apply Lenz's law. Not so much if it's just Faraday. So if you want a quick recap, Faraday's law states that the induced EMF, let's say I give it a symbol E, is directly proportional to the flux dt. But what is the flux dt? Rate of change of flux. So what Faraday's idea is, as long as your flux is changing, you have an EMF. So flux would be, let's say you imagine, okay, let us draw some magnetic field lines. Since we don't know which is north and which is south pole, well, I'm not going to draw a direction first, I guess. So I think you can tell that there will be plenty field lines between this. Okay, so all these blue color lines are your magnetic flux. So as the metal disc go in this way, let's say we'll go in like this, it will cut the flux, or the better term would be the flux inside this metal disc. The flux inside this yellow color metal disc will go from no flux, because at this position there are no blue lines entering this yellow area, to got flux. So you imagine as this swing in between the pole of the magnets, the flux that passes through the yellow color area will increase. So the flux will change. So as long as there's flux change, there will be EMF. So this will be the first part of the question. State Faraday's law of electromagnetic induction and use the law to explain why an EMF is induced. So I will start first by stating what causes the flux change. Step 1, identify, is there a flux change and where does it occur? So I will say as the metal disc enters the area between the two pole pieces, it experiences a change in magnetic flux. So normally if you write flux itself, it is understood that it's magnetic flux linkage. But if you want to be thorough, especially if all these terms are still new to you, I will encourage you to write the whole term. Magnetic flux linkage, symbol here is psi, okay? So what did Faraday's law say? So you could say, since Faraday's law states that the EMF induced in a circuit, Miss got circuit meh? Your metal disc consists of many charge carriers. So you can assume that your metal disc has many loops like this. These are all circuits. So this one, all many loops. I will call these wires. Okay, loop to form a disc. Because what a wire is just a thin piece of metal. All right. So states that the EMF induced in a closed loop is directly proportional to the rate of change of flux. Use the symbol again, or magnetic flux linkage. So that's why, hence, current or EMF is induced in the disk. So the 2 marks here, of course, one would be a Faraday's law statement. Faraday's law states that EMF induced is directly proportional to the rate of change of flux. Okay? And as the metal disc enters the pole pieces or swings into the pole pieces, you mentioned that this metal disc experiences a change in magnetic flux. Okay? So that would be 1 mark each. Part 2. Explain why eddy current are induced in the metal disc. Okay, so when you want to think about eddy currents, right? Eddy current is a pretty specific pattern of current. All right, I'm gonna give this a beautiful shade of pink. Okay, so this eddy current, right? It occurs whenever you have something that is not wire. So anything with a large surface area, it can be a metal disc, it can be like a 3D metal cube. So anything where your charge density is high because you have a large area, okay, this will allow eddy current to form. So since we can assume that the metal disc, this metal disc here, is kind of like the same as there all these many wires looped together. So the eddy current, right, actually take the form of something like this. Okay, so let's look at this current, this diagram for a bit. You see that this piece of metal, okay, is traveling in this direction. So if the piece of metal is traveling in this direction, it is experiencing a change in flux. So the flux inside the metal pieces will change. And as you can see, there's eddy current, and this eddy current, they look very loop-like. And you might observe a few things. Number one, I noticed that the eddy current here, where I'm circling, the field lines here are very close. So here you will have a larger EMF. Here the electric field is larger. Then here the electric field is not as large. Or I guess you could see that the current is not uniform. You get this weird circular shape of current. Okay? So there's a lot more to this, but this is a very unique pattern. So we call this eddy current. All right. So the reason why we have this eddy current is to oppose the field change. So for example, you will notice that this field here, this red color field, is inducing a downward magnetic field. It's like, I want this magnetic field. Miss, how do you know this B induced due to this I induced is going downwards? Well, we use the right hand grip, right? So when you use your right hand grip rule, we follow this. Okay, I'm using, give me a second. Okay, so if you follow this, your finger will point this way, right? Point towards the screen, turn out away from the screen. Look at my mouth and look at my hand, point into the screen, turn out away from the screen. So when you curl this way, into and out, your thumb is pointing downwards. Use your right hand grip rule, you see your B is going down. So this is accordance to Lenz's law. When this metal sheet is about to run away from the magnet, the metal sheet on this yellow portion experiences a decrease in magnetic flux. This one here, this part here will have a decrease in magnetic flux. And the green color flux, this green color flux. And you know the whole idea of Lenz's law is that the current will flow in such a way to oppose the change. So if, let's say, for example, your change is to decrease, then the current is like, no, I don't want to decrease. I want to make back the green color field that you have taken away from me. So this B induced is to attempt to increase the decreasing flux. Okay. So basically when this one moves in this direction, step 1. Step 2, there's a decrease in flux of the metal sheet. Okay. Step 3, current is induced according to Faraday. Step 4, this current induced will flow in such a way to oppose the change. So what was your change? Your change was you have lost this green color magnetic field. You're like, I want to make back this green color field in the same direction, so the current will flow in this counterclockwise direction. Okay, so this is what is happening here. 1, 2, 3, 4. All right. So sometimes explanation wise, you only need to explain until step 3. As the metal sheet moves in this direction, there's a decrease in flux. And because of this, according to Faraday, current is induced. But sometimes we need to bring in lengths. We bring in lengths when they ask us to explain the direction of the current flow. Why is this current flowing in this direction? Well, this is because it's trying to make back the magnetic field that was once missing. Because it had a magnetic field a few seconds ago, right? Now you pull it out from under, then it's no more already. All right. The second thing that you will notice is the part at the back, which I'm about to change color. So maybe I'll just highlight this part blue. At this part, you will notice that the direction of current flow is opposite, meaning the direction of induced magnetic field is now pointing upwards. Be induced. Okay. Why is that? For the opposite reason, but the same laws as the yellow color region. Because for this blue color region, it is about to enter or is on the way of entering this side. So first step, you will say as the metal sheet passes through or enters the pole of the magnet. Number 2, this portion here, there's an increase in flux of the sheet. The metal sheet, the metal piece, the metal disc, whatever lah, okay? So because you have this change in flux, then the metal sheet is like, hey, I don't have magnetic flux in the beginning. And then you increase my magnetic flux. I don't like this increase. I don't like this increase. This means, number 3, there will be a current or e.m.f. induced according to Faraday. And number 4, this induced current will flow in the opposite, will allow magnetic field, because it will flow in the opposite direction here. So it will allow magnetic field to be smaller, or it will induce its own magnetic field to fight the increase. So you will say that this one, the current is induced and flows in such a way, as you can see here, current flow to induce this upward magnetic field, okay, to decrease the increasing flux. Wow, so means there's many eddy current, no? Yeah, no? So as the metal sheet passes through and cut the flux, what exactly is happening is when this metal sheet suffers through a change, whether it's a decrease for the yellow portion or an increase for the blue portion, current will flow inside the metal sheet to try to oppose the decrease. So if the yellow portion, you are taking away the magnetic flux from the yellow portion don't like, it makes its own magnetic field flux in the same direction. For the blue portion, it didn't have magnetic flux in the beginning. You pull it in between the poles, from here to here, you pull it in. Then this one is like, I don't like this green color magnetic flux, so I'm going to make my blue one to oppose it. So this is Lenz's law. Lenz is all about opposing change. You increase, I don't like, I will decrease it back. You decrease, I don't like, I will increase it back. All right? So that is the idea of the direction. Meaning to say, the way this current will flow, it flows in a particular coil-like fashion. Of course, if you want to decide whether this, how you want to draw out in this diagram, what you could do is you have to decide which one is north and which one is south lah. So let's say I decide that this is north, this is south. Again, it's up to you or your discretion. So if I do so, then from the perspective of the metal disc, I'm just going to draw here so you can see, okay? So when the metal disc is here, it has no flux. When it passes through here, suddenly it has this inward, the magnetic flux that's going into the screen. Okay, into the screen would be cross. This is a B. Okay, so imagine I put my eye here and I look at them. So here, at this point, there is no field. And then at this point, there's this field. So from number 1 to number 2, there's an increase in flux. Flux increase. I don't like this increase. Why suddenly give me this cross magnetic field? I would like to oppose this magnetic field. So how do I oppose the magnetic field? I will flow current in the opposite to create an opposite field. So what is the induced opposite field? It has to be pointing out of the screen. Okay, so I'm just gonna put a legend here for you. This cross here is the magnetic flux, or the flux from the pole piece, and the dot is the induced magnetic field to oppose the flux increase. Of course, in case you don't know or you don't remember, flux is equal to NBA, okay? In this case, it will be equal to BA lah, because there's no coil. Okay? So this means if I want the current to go, the current to flow, it needs to create a magnetic field that is going in the opposite direction. So the magnetic field induced has to flow like this. Sorry, has to flow like this to oppose this one. It has to flow in this way to oppose this one. All right. Okay, so if you really just want to determine the direction of the eddy current, whether it's clockwise or counterclockwise, you could take out your right hand grip. Thumb will point away from the screen towards your eye. You will find that you are coiling from your perspective counterclockwise. So the direction of current flow. So if I want to draw the eddy current will look like this. No? Counterclockwise. Counterclockwise. I draw two enough already, but there are many, many loops. Okay, but what causes this eddy current? Because it's not just a change in flux, it's also because of the shape of the metal disc. Okay, when you're talking about a metal disc, right, the motion of the oscillating thing already have a different speed or a different change. So on one side it increase, on the other side it decrease, or let's say it looks something like this, right? Then what will happen is that you get this swirly current shape because it keeps changing. You think about this, the next second later, the disc will be here. And then it's about to exit now. So it's going to go from I had a flux to I have no flux. So if it goes from I had a flux to I have no flux, then the current will change direction again. So the current keeps changing direction, no? And it's like that circular part. So that is what is known as eddy current. Okay, that kind of swirly shape. Of course, if you are good in, or if you do some further maths, you will understand that here we need to actually apply a lot of calculus. But we're just trying to explain the concept, okay? So why is eddy current induced in the disc? We need to talk about the shape of the metal disc. So you could say that due to a large surface area, because wire don't have large surface area, okay? You can say that the e.m.f. induced in different parts of the disc is not the same. Okay? And this is also because the rate of change in flux, okay lah, right, full in flux is not the same at every part due to the different speeds. This thing is still in a simple harmonic motion. So they will have different speed as they oscillate differently. All right. And finally, use energy principles to explain why the disk comes to rest after a few oscillations. So when you think about having current inside your circuit, right? What is happening here is you suddenly have electrical energy. You got current in your circuit, right? So it's like, don't know from what, we had electrical energy. And of course, I will expect as it flows inside the metal disc, there will be resistance. And then in the end of the day, it will become heat or thermal energy. But where did this electrical energy come from? The thing is oscillating. So it came from the mechanical energy of oscillation. So if you remember in your oscillation, the energy of oscillation here would be your half ma square omega square, which is a combination of kinetic energy of the disk plus the potential energy, gravitational potential energy. So what we can say is that the energy of oscillation is converted or transferred to electrical energy of the eddy current. All right. This energy is eventually dissipated as heat or thermal energy to the surroundings. 2 points. Where do you think the third point is? It says here that we are talking about it coming to rest. So if it comes to rest, it means that the amplitude of the oscillation will be 0. Or so then what I can say is, since the amplitude of oscillation is related to the energy of oscillation. You want to flex a bit, you can write the equation lah, but I'm not going to. The amplitude decreases and becomes 0. So become 0 means the oscillation has stopped or it is at rest. Okay, so this is the entire question. It is an old question, but it's talking about a main idea about breaking or stopping something that is moving. Because this energy of oscillation is also the combination of kinetic energy. So it allows us to create this thing called an electromagnetic or eddy current, a braking system. Okay, break or stop. So I'm just going to show you this demonstration, this short clip demonstration that I found on YouTube. If you want to watch the whole video and listen to the really great explanation, you can find the link in the description. Okay, so you can see that this is oscillating freely. Okay, there's a free oscillation in between. But once we put the 2 electromagnets, observe the oscillation. Previously it was swinging very energetically, and then you can see now it has stopped. Okay, so the reason why it has stopped is because the energy of oscillation is quickly taken away due to eddy current. All right, so that is electromagnetic braking. Okay, so that's it about eddy current. Eddy current is very useful when we want to dissipate energy from the system very quickly. Something is moving too fast and we want to slow it down very quickly. Okay, so it's way more efficient than, say, using friction, because friction will cause the surface to smoothen out and you need to replace certain things. It's way more safer than using something like a hydraulic brake, because the hydraulic brake can leak and also need to be replaced. But of course, it all has its place inside the world of machineries in our life. So same thing for eddy current. It also has its place. It is able to stop things that are moving very quickly, like roller coasters or trains or I guess cars as well. We can employ all of this electromagnetic system to slow things down. So there are certain examples where we don't want eddy current, or it becomes a reason why there is an inefficiency in our circuit. So this is when electrical energy, we want to keep it as electrical energy, but it went out as heat, or we want to minimize eddy current. So this is in transformers. We will talk more about that in the transformer video. So hopefully you find this video helpful, explaining to you what an eddy current is, how Faraday and Lenz's law is applied in eddy current. Okay, being able to visualize the coils or the swirl of eddy current that allows a surface, a piece of metal or a block of metal to heat up and also to slow down. So if, let's say, I allow this fast moving sheet of metal to pass through strong magnets, this fast moving sheet will actually slow down. So it's a lot like braking a rotating disc. So for example, this one could be like a car emergency brake. All right, so I think that's all. Thanks for watching this video. I hope you find this helpful. Share us with your friends, like and subscribe. You know what to do, and I'll see you in the next one. Take care now.